So this is intended to be a quick summary of the types of reactions that you can expect to use throughout organic chemistry, and then taking a step further, the individual mechanistic steps that can potentially happen and what kind of names we'll call them. So you need to be familiar with these. That's why we're going to kind of whip through this fast. But I just want you to be aware of them, and then we'll start to use them in future chapters. So there's 5 main types of reactions summarized here. Okay, we've already talked about acid-base chemistry. What you're looking for is only the transfer of a hydrogen. So remember, when I talk about it, we're referring to acids and bases purely as the Bronsted-Lowry definition, so only the transfer of a hydrogen. And you can see in this reaction that what ends up changing in the course is that that location of the hydrogen has shifted from one substrate to another. The next part of this is a substitution reaction. So this is an exchange or a transfer of an atom other than hydrogen. And that would be it. So if we go through and take a look at this, what you should see is that we are exchanging the leaving group for the nucleophile, or sorry, the LG for the NUC, which is leaving group and nucleophile, as we'll discuss later. You notice that they've swapped places, so they've substituted for each other. You might draw parallels with the substitution reaction to a double replacement that you've seen in Gen Chem. The next style of a reaction is an elimination reaction, and what this is the result of 2 sigma bonds breaking and the formation of 1 pi bond. Okay? And in all of these cases, ultimately what we're looking at is around our carbon structure or our substrate. Okay? So in the case of this reaction, those 2 bonds are broken, and as a result we can form a pi bond on our substrate. Okay, so that's our big difference. So we're looking for the formation of that double bond, or sorry, pi bond. So if you see a pi bond being formed, elimination reaction. The opposite of an elimination reaction is an addition. So it's the loss of a pi bond resulting in the formation of 2 new sigma bonds. So if we take a look again, our pi bond starts in our starting material, and if we look at the result, we no longer have the pi bond, but we have 2 new sigma bonds, 2 new bonds that have shown up in our structure. So it's helpful to be able to identify these types of reactions, because that can help you then go through and predict what kind of reagents you need to use. If you know it's an elimination or a reaction, you might be looking for a base. If you know it's a substitution, then you want to look for a nucleophile. So it can limit some of the searching through your brain stores for reagents later on. So it's important to get these nailed down, find the patterns, make sure you know them. I will say there is a 5th one on here, which is my least favorite, but it can be actually interesting because it does lots of bizarre chemistry, and that's the radical reaction. Not as important for most of this semester. We'll probably see that the very last week of class. So don't stress about that right now. Keep your focus primarily on these 4 types of reactions and ultimately the mechanistic steps that go with them. So as you remember from 152, you've got mechanisms for reactions. When we look at kinetics, how fast does a reaction occur? And we could reference our slowest step of the reaction as determining our rate. So we have to know something about what steps are involved in the reaction. Those were referred to as elementary steps. So in Chapter 7, what they do is they summarize what the elementary steps are, and they've put them into individual sections. They haven't numbered them. I attempted to number them, so we'll see how well that works. What we end up doing is in future chapters, we then look at a new reaction. We say, okay, what are the elementary steps that went into it? If you know the elementary steps, that helps you predict certain features of the reaction. Is it fast? Is it slow? Is it slower than this reaction? Okay? So it gives you something to then play around with and start to predict the feasibility of a reaction if you know something about how that mechanism is supposed to work. There's really 2 aspects to this. You get, and again, this is for our main 4 reaction types, you get heterolytic bond cleavage. So all we're saying is we're breaking a bond, and then you can get bond formation. Okay? So those are the 2 big concepts. It's now a question of what's happening or what features of our structure are present when we go through and do this. Probably the more important or the most important one is that first one on our list, is if our heterolytic bond cleavage and bond formation happens at once. Okay, so I've labeled that as simultaneous, and I'm just saying that's step, or that's type 1. Well, type 1 does classify for multiple types of reactions. We can look at an acid-base reaction, we can look at what's known as an SN2, which we'll get into the details of that, and an E2. So if your bond breaking and forming happens at once, simultaneous, we've got that type of mechanistic step. Everything's happening together. If it doesn't happen at once, then we can start to see some kind of variances from this. That's where you get heterolysis, so break the bond first, that's an elementary step, okay, followed by coordination, and I'm pretty sure I've got these labeled this way, followed by coordination as a possibility for the bond formation. So these are now 2 distinct steps, so we'll number them as such. So we now have 3 possible steps. After that, we can start to move into separating out our addition and elimination reactions according to what type of materials are involved. So in steps 4 and 5, we're looking at electrophilic addition, right, or electrophile elimination. So we're looking at an addition reaction, meaning the loss of a pi bond, okay, loss of pi, versus an elimination, which is the formation of a pi bond. Okay, so how the loss of the pi bond or the formation of the pi bond occurs is going to determine whether we're looking at electrophilic or nucleophilic ultimately, or electrophile versus nucleophile. So what we're talking about in each of those cases has to do with what other pieces are floating around. So if we happen to look and we identify an electrophile and we see the loss of a pi bond, well, we're looking at an electrophilic addition type reaction. So it's a question of piecing those pieces, or finding that those pieces of information to put them together. The last set, which I've got labeled as 6 and 7, are your nucleophilic addition and nucleophile elimination. So it's the same type of reaction, addition and elimination, as the previous one, except now the extraneous piece that's floating around in solution is going to be a nucleophile or something nucleophilic, not an electrophile. Okay, so by identifying our nucleophiles and electrophiles, which is what we talked about in Chapter 6 and to a larger extent in Chapter 7, that can then help us decide what type of mechanistic step we're working with, which allows us to then propagate and predict a lot better. So, as some examples, in your simultaneous elementary step, you're looking at bond cleavage and bond formation happening at the exact same time. That means that all of the curved arrows we would add by using a mechanism have to happen at the exact same instant. So in that first reaction, we're noticing the change of the location of the hydrogen. Well, I have to form the new bond between the nitrogen and the hydrogen at the same time as I break, actually let's color code, actually I'm going to color code this way, at the same time as I break the oxygen-hydrogen bond. So if I'm going to add curved arrows into my reaction, what I'll do is show that the electrons from the nitrogen share with the hydrogen, making that new bond, while at the same time breaking the bond between the oxygen and the hydrogen. So now what I've done is my elementary step. It's as simple, quote-unquote, as that. If we go through and look at the next reaction, that's our substitution type reaction, because we're looking at the exchange of iodine for bromine. You'll notice that what I've circled is only on the substrate. Only on the substrate because this is organic chemistry. I only care about the organic molecule-ish. Okay, so let's focus around that and see what happened. Okay, well, I had to break the bond between the carbon and the bromine, and I had to make the bond between the iodine and the carbon. So what I need to go through and do is show all of that happening at one step. Well, the iodine, with its negative charge, will share electrons with the carbon, but at the same time I need to break the bond between the carbon and the bromine. And I know this is happening at the same time because all of my arrows are in one reaction step. Okay, so that's what our arrows in between are showing. That is a reaction step. If these things were happening in multiple steps, I'd have multiple sets of arrows continuing on down the line. Since I don't, this is only one step. In the last case, we've got a lot of things going on here, and depending on how you want to look at it, we can say different things. But we've got the formation of the pi bond at the exact same instant that I have the breaking of that carbon Lg group, and I have the breaking of the hydrogen carbon group. Okay, so if I'm going to try and represent all of that appropriately, okay, other things that we could look for is that you notice that our hydrogen has changed location as well, is that we're going to take the electrons from our carbon Lg group and have those leave. Okay, so the Lg takes the electrons. At the same time, our base comes in, shares electrons with that hydrogen. Well, now the hydrogen has too many electrons, and the electrons in that bond can then go to make our pi bond. Okay, so an added level of difficulty with the elimination, because we actually have a bunch of different things happening here. This is still officially an E2 step. Okay, and what might be confusing about that is you'll notice that we did exchange the location of a hydrogen ion, okay, which would suggest acid-base. However, it was not the only thing that happened in this mechanistic step. Because it is not the only thing, we do not reference this as an acid-base reaction, but as an elimination step. Okay? So it's a question of seeing what happens across the reaction and saying these are our mechanistic steps behind it. So, if we take a closer look at our substitution, we had this Lg and our nuke system showing up. You'll notice that I've got nucleophile/base. Our Lg is our leaving group because it is the group that leaves with the electrons. Remember, if we think back to the arrows that we drew over the previous system, our leaving group took the electrons in that carbon leaving group bond, so it left with electrons. Okay? And that's going to end up breaking a bond. Our nucleophile or base is the one that is supplying electrons. Okay? So it's making the bond. So it's going to have to share electrons. So things that we might kind of parallel out of this, our nucleophile probably needs to have electrons. So you might look for a negatively charged species. Our leaving group needs to take electrons from carbon. So whatever our leaving group is probably electronegative because it needs to take the electrons away from carbon. So it needs to be more electronegative. So some examples that we could potentially see here. In this case, we're doing a substitution reaction of chloride for OH. So we've converted an alkyl halide, an alkyl chloride, into an alcohol by showing those arrows. Okay, and you'll notice it's all happening in one mechanistic step, and we know it's one step because when we're drawing out our mechanism, we only see one reaction arrow. Okay, that's how we know it's only one step. Your textbook goes through and gives you a variety of other examples. So we can see larger and more different groups happening in each case, and just because it's bigger doesn't change its functionality. So in this case, what ends up happening is the atom supplying our electrons, our nucleophile, attacks, while at the same time our leaving group takes electrons. Okay, well, the leaving group then is whatever is no longer attached to our carbon, which is now a very, very large group. Okay, so size is irrelevant. We're only looking at forming the bond or breaking the bond. So ignore size, just look to see what bonds change. The size is just there to mess with your head. Okay? What do we got? Elimination. Elimination, you'll notice, follows very similar patterns. We still have a leaving group, but now instead of saying a nucleophile, we have a base. Why do we need a base? Well, what supplies the electrons to make the pi bond? A pi bond needs 4 electrons between our 2 carbon atoms. Right now, there's only 2 electrons there. We need to have 4. That extra pair of electrons comes from the carbon stealing electrons from a hydrogen. So that hydrogen can't just float off into solution on its own, depending on who you talk to. and that's where the base comes in, supplies electrons to the hydrogen to make sure the hydrogen doesn't come off as H+. It's now stabilized in solution. Okay? So that's our overall result. So we can go through and look at this one. We again have a nucleophile. We again have our leaving group. Whoops, it's not a nucleophile in this case, this is a base. As you might notice, one of the things that we said about a nucleophile is it's very often negative. Well, what charge would we expect of a base? To react with a positive hydrogen, it's often negative. Okay, this is an added complication that we will address when we start looking at these mechanisms in more detail. Okay. And again, we've got some more complex systems going on with this. You'll notice that we can again use a much larger leaving group. It does not have to be tiny, so we got a pretty large leaving group in that case. And you'll notice that in the bottom case, we are still doing an elimination reaction because we are forming a new pi bond. Okay, I don't like that they say triple. We're forming a pi bond. Yes, there's already a pi bond there, and the net result is that I have a triple bond, but ultimately the change is that I made one new pi bond, period. So focus on the patterns of what's happening out of it. We'll stress more about the details when we get to those types of reactions, and we evaluate those reactions in detail. After that, we can run into now stepped mechanisms. So now we're going to have multiple reaction arrows to get us all the way through to a final product. Okay, so we've got heterolysis, the bond breaking, which usually involves the formation of high energy intermediates. And then we follow that with coordination, which usually neutralizes the reactivity. Okay? So if we take a look at these individual steps, we want to go through and try and decide what's happening. So in this first case, we've only got one step, and what's happening? Well, I'm taking the electrons in the bond between the carbon and the iodine, and I'm putting them solely on the iodine. I now have iodide and a carbocation. Okay, well, are these products expected to be higher in energy or lower in energy than our reactants? Hopefully you see that they're higher in energy because they are charged. Okay, that charge then says those are higher in energy, so we're now forming a high energy intermediate. That intermediate suggests that we now have a heterolysis reaction. If we move to the next example, we've got a similar situation. We also have a heterolysis. Okay. I'll let you take a look at that last example, try and come up with your own decision, and if you've got questions in class, when we go through it real fast in class as a review, you can go ahead and ping me then. Intermediates. This becomes a problem because we can form carbocations, and if we think back to when we talked about mass spec, we have to worry about stability of carbocations. Okay? So we've got our zero area, our primary, our secondary, and our tertiary. Our zero area is extremely unstable, and our primary is extremely unstable. Those are so unstable that we do not form. Okay? So we don't have to worry about those. So mechanistically, we don't see them. If, however, we form a secondary near a tertiary, now we've got a problem. Okay? Tertiary is ultimately much more stable than the secondary, and as a sort of repercussion of this, what we end up getting is something known as a rearrangement. What will end up happening is we will shift groups around, okay, in the immediate vicinity to stabilize or form a more stable carbocation. So if we went through and said in this group, or in this reaction, that we have carbons as 1 and 2, what was the net result? Well, I started with a carbocation that was attached to just 2 carbons, which means it was secondary. And as a result, if I look at where my carbocation is now, I now have a tertiary. So as a result of the shift, I end up with a tertiary carbocation. That result is that I take the electrons in that bond and I move them to the carbocation. Not to a bond, but to the carbocation atom itself. The result is that I've taken the shifting group and I've now placed it onto the carbocation containing group. Okay. This does result in a shift of charge and an apparent motion of the positive charge. That is not true. The positive charge does not move. What moves are the electrons, and what we end up seeing is a new positive charge appearing. You can't move positive, you can only move negative. There are a ton of different examples on this. We will go through this in a lot more detail and a lot slower in class. You can get a hydride shift. If your shifting group is a hydrogen atom, it's called a hydride, and that's known as a hydride shift. We could also do a methyl shift. Right? Those are the two most common ones you'll see, but it can really be any carbon group or any group period that can shift. In step 4, for our step reaction, we have an electrophilic addition. Our pi bond will act as our source of electrons and will attack an electrophilic atom. This results in the loss of a pi bond, hence our addition term. The electrophilic is coming in because the pi bond reacts with an electrophile. Okay, so it's an electrophilic addition. Both of these reactions were specified in your textbook as electrophilic addition reactions. What I want you to do is to think about that second one a little bit closer and tell me why that might be a little bit weird to refer to that as an electrophilic addition. But ultimately it's the same kind of idea. In an electrophile elimination, okay, this is the reverse of the electrophilic addition. In electrophile, most commonly hydrogen, which is also a little bit weird, is removed from the substrate, allowing for the formation of a pi bond. Okay? So hydrogen, our electrophile, typically carries a positive charge. So we refer to this as electrophile elimination because the electrophile has been kicked out of the group, okay, or kicked out of the structure, resulting in the formation of a pi bond. Okay, so this type of mechanistic step is known as electrophile elimination. You'll notice that we really only show one arrow for this result. Okay, it's just the loss of that group, and the result is the formation of our new pi bond. Step 6, we're looking at a nucleophilic addition. This is where a nucleophile will attack an electron-deficient atom of a polar pi bond. Okay, so your nucleophilic additions and ultimately eliminations are happening around pi bonds that are very polar. If you go back and take a look at the examples of our electrophile elimination and our electrophilic addition, you'll notice that we're not looking at polar pi bonds. We're looking at carbon-carbon bonds that are breaking and forming. Okay. When we move to nucleophilic addition, okay, our dynamic changes, and we're now looking at the breaking of a polar pi bond. So carbonyls is our biggest option here, but we can sometimes see it with carbon-nitrogen double and triple bonds. Okay. The dynamic that changes in this case is that the pi bond is ultimately kind of acting as our electrophile, because our nucleophile comes in and supplies electrons to the electron deficient atom. We know it's electron deficient because if we look at the least worst resonance structure, the carbon is positive and our oxygen is negative. Okay, so resonance can help us predict what's happening with our nucleophilic additions. Oh, and I may have lost my internet connection. So we'll see what happens. Maybe it's there. The last one is our nucleophilic or nucleophile elimination. So this is the reverse of our nucleophilic addition. The nucleophile leaves the substrate, resulting in the formation of a pi bond. Okay? This means that we had to have our nucleophile leave with the electrons. It's effectively acting as a leaving group, not as a nucleophile. Okay? So we're looking at what is the result of that. The result is I have this chloride, which is a nucleophile, because it is negatively charged. So because I've now kicked off that negatively charged structure and I've formed a pi bond, okay, make sure I didn't erase that too much, we have a nucleophilic or nucleophile elimination. So those are our 7 mechanistic steps. Okay, when we get into class, I do expect questions on it when we talk about it in lecture. I'll go through it a little bit slower, but I really want you to at least have the basics down before we talk about it in class. Hopefully you watch it. Just to be mean, let's go ahead and say there's a quiz, and on that quiz we're going to have a secret code word. That secret code word is going to be red. Okay, so you need to know that secret code word for the quiz that we will have in class when we talk about this. So hopefully you watched the video all the way through, and now we're just going to erase it, so that way you can't just watch the very end of the video because you won't have seen it. Haha, mystery. Yeah, I guess that's it.